So the first step you have to do here is you have to find the days. If you look up October 28th, what date does that come out to be on our calendar? What's that? 301. Perfect. And of course, January 8th is day 8. Step 1 is to find the maturity value of the original note. So we're going to find our interest, which is going to use the principal of $7,000 times our rate. 7.4% becomes 0.074. And our time, 120 over 360. Giving us 172.67 is our interest. Now the maturity value, add that $7,000 principal back to it. $7,172.67. What's step 2? Yes, we need to find the discount period. We need to worry about the days. So we're at day 301 there. So what we need to do is do 365 minus 301, 64 days. Plus the 8 days into January is 72 days. Is that our discount period? Say no. No, what do we still have to do? We have to subtract from the full term of 120. 72 days are the days that have gone by. We want the days that are left. There's 48 days left. So that is our discount period, the 48 days left. Now we figure out the bank's discount. So that interest is going to be the maturity value of 71.7267 times the discount rate, which was 8.8%, so 0.088, times that 48 days over 360. Giving us $84.16. That's what the bank charges for holding that loan for that last 48 days. So then the last step is the proceeds. Proceeds is going to be the maturity value minus that $84 in interest. So we get what, 51, 7088.51. That's the proceeds. That's Jordan's proceeds. Any questions on that one? Okay, well then. Yeah, that's the big step right here. A lot of people want to try to use that 72 and that don't work. Pat borrows, well, $7,000 has been working good for us. $7,000 for 120 days at, well, let's go 7.4% on a, now the last one was an SIN, which stood for simple interest note. This is an SDN that stands for simple discount note. I want you to find the effective rate. So I'm gonna give you a couple minutes to work. Step 1, find the discount. We do that by basically it's just the interest. 7,000 times 0.074 times 120 over 360. 172.67. Does that look right? Next, we find the proceeds. That's going to be the 7,000 minus the 172.67. So $6,827.33. Now we find the effective rate using I equals PRT. So I is the 172.67. P is the proceeds of 6827.33. We are looking for R, and our time is 120 over 360. So we are going to combine the 6827.33 with the 120 over 360. We multiply that out, we get 2275.78. Now again, this is one where I'm going to keep this in the calculator so that I don't have to, if I were writing it down and I was going to type it back in, I'd want to go for 5 or 6 decimal places there. I got 7.8. So now I need to divide by that 2275.78. And the way I'm going to do that to avoid round off error is I'm going to type in the 172.67 and I'm going to divide by that previous answer. So use the second answer function of the calculator. And I get 0.0. Now remember, we're going to go at least 5. It's usually preferable to go 6 digits here. 0.075873 equals R. Now I have to make that a percent. I have to go 1, 2. So it's 7.5873%. And we're going to round it to, if we're not told, we're going to round it to 100th of a percent. So right there. So that's 7.59%. How many of you had that? Good. We're coming along on those. So as we mentioned, so far what we've been talking about is simple interest. And I know we talked about this a little bit at the end last time, but in simple interest, there's one payment in, and then there is one period where interest is earned, and then there's one payment out, money coming out. Whether it's an investment or a loan or whatever. This week, we're going to talk about compound interest. Compound interest, you still only have money coming in at the beginning and money coming out at the end. There's no other payments in the middle there. But rather than the interest being calculated over one long period, the interest is calculated over several preset periods. And that's what the compound means, is any interest earned in this first period now becomes part of the principal for the second period, and you earn interest on top of that. So let's take some time here to develop, well, some vocabulary first of all. The amount of money at the beginning of the term is called the present value. The amount of money at the end of the term is called the future value. And of course, the interest earned is referred to as the compound interest. So let's take a look at developing this formula. We had, let's say, Chris invests $8,000 at 6%. We're going to start out 6% simple interest. For 3 years. Let's find that maturity value or that future value. Well, the interest, this says simple interest, so we're still using that simple interest formula, is 8,000 times 0.06 times 3. Ends up being $1,440 in interest, which means the maturity value or the future value is $8,000 plus that interest of $1,440, so $9,440. But as we know, most banks, most financial institutions don't like to do simple interest on something that long. Usually 6 months is the maximum they would do simple interest on. Many institutions won't go more than 3 months without compound interest. So let's look at the comparison here. Kim invests $8,000, also at 6%. But instead of simple interest, this is compounded quarterly for 3 years. So the big difference here is that phrase, compounded quarterly. What does that mean? Every quarter, every 3 months, they're going to figure out the interest, they're going to add it to the balance, and then you're going to get interest on top of that the next quarter. How many quarters are going to be in 3 years? Yeah, 3 times 4 is 12 quarters. Referred to as 12 periods. Well, let's take a look at how this would work out, or start at least working this out. So we're going to go quarter by quarter, finding the interest and the ending balance. In quarter 1, the interest is 8,000 times 0.06 times 1 quarter, a quarter of the year. That's $120. Does that look right? So that means our ending balance is $8,120. We just added that to the original $8,000. In quarter 2, our principal is $8,120 times 0.06 times 1/4. Give us $121.80 in interest. So that means we have $8,241.80 is our ending balance. So we would start quarter 3 with $8,241.80. Are you guys still able to see my computer screen? No? Thank you. Now, I'm not going to keep doing this because how many times would I have to do this? 12. I don't want to do this 12 times. So let's take a look at what is happening each of these times. First of all, let's look at this right here. Notice that's 0.06 times 1/4. That appears in each of those interest calculations. 0.06 times 1/4 is 0.015. What does that really mean? Well, it's 6% per year. It's 6% annual interest. So what that means is it is 6 times 1/4, or divided by 4, it's 1.5% quarterly interest. So that is the interest per quarter is 1.5% or 0.015. Now each period here, we took the principal plus interest to get the maturity value. Kind of like when we were doing our markups or our percent increases from before. The principal is 100%. What we added each quarter is 1.5%. So the value at the end of the quarter is 100 plus 1.5, or 101.5%. So what that means is to find the balance at the end of the quarter, we could take the beginning balance times 101.5%. Let me show you. The first quarter, we started out at 8,000. As a rate, 101.5 is 1.015. That comes from the 101.5%. That gives us $8,120. The second quarter, you take that $8,120 times 1.015, that would be the $8,241.80. Notice those are giving us the same ending balances. Well, how many times do we have to multiply by 1.015? 12, right? There's 12 of them. So that's $8,120 times 1.015, 12 times. Well, in math, we have a shortcut for that. It's an exponent. Oops, I shouldn't be 8120. It should be just the 8,000. Okay, starting balance times the 1.015, 12 times. Which is 9564.95. Compare that to the 94.40 that you had from simple interest. That's $125 more. Yes, sir. You either have a caret key that looks like that, or a y to the x or x to the y key. Y to the x, yeah, that should do it. So you type in the 1.015 yx12. Okay. Let's take a look at where this really comes from. What this is the future value formula. Remember, future value is the amount you'll have at the end of the term. N is defined to be the number of periods in 1 year. So our future value is equal to the present value. Now the present value is the value at the beginning of the term times, now I'm going to warn you a little bit up front, over the next 3 weeks we're going to have some very seriously long formulas. So you may want to find a spot in your notes where you can put all these formulas so you have them, so you can refer to them rather quickly. Leave space to give yourself a little bit of an explanation as to what, when do you use each formula and what do the things mean. But the future value is equal to the present value times 1 plus R, which is your rate, that's your percent as a decimal, divided by N, which is your number of periods in a year, to the power of N times T. So what does all this stuff mean? That 1, like up here, that was from the 100%. Then the R over N, that was that 1.5%. That was the annual rate divided by the number of periods in a year. The N times T, T is your number of years, so N is your number of periods per year. Multiplying that out, that's your number of periods. In the previous example, it was quarterly, so N was 4. T was 3 years, so we did 4 times 3 to get the 12 periods. Yep. Future value is the balance at the end of the term. Present value is the value at the beginning of the term. N is the number of periods in 1 year. So quarterly, it would be 4. Monthly, it would be 12. Semi-annually, it would be 2. Annually, it would be 1. R, again, is your rate as a decimal, your percent as a decimal. And T is your number of years. Yep, NT is part of the equation. Yes, that is R over N. The rate, that's your percent as a decimal. That's an exponent. But yes, it's N is the same N and T is your years. Let's say Alex invests $2,500 at 9% compounded monthly for 5 years. Find the ending balance. The ending balance, of course, is the future value, balance at the end. To find the future value, we need the present value, which is 2,500 times parentheses. Now, 1 is just part of the formula. That's from the 100%. Plus, what's our rate here? 0.09. 9% becomes 0.09 as a decimal. And that's going to be divided by monthly means how many periods in a year? Careful, you're thinking quarterly. 12, there you go. So divided by 12, that closes our parentheses. Our power then is 12, that's N still, times 5. Now I wrote that up high, so I've got room to write it in. What is 12 times 5? 60, right? It's usually easiest if we figure out that number of periods before we start typing this in the calculator. So that means we have 2,500 times parentheses 1 plus 0.09 divided by 12, close our parentheses, to the power of 60. So 3,914.20. That is the future value. At the end of 5 years, that would be the balance in Alex's account. What do you think? Not too bad? Did you get to work? Yep. So 2,500 times, open parentheses, 1 plus 0.09 divided by 12, close parentheses, to the power of 60. $3914.20. Everybody get to work? What's that? Showed 0? Here, I'll come on over quick. So, let's look at a slight. Yep. Sure. Let's do another one. No problem. Pat borrows $8,300 at 7.4% compounded quarterly for 4 years. Find the maturity value. It is the same, just different numbers. I'll give you a minute to try this one in your notes. Let's take a look. So our future value is 8,300 times, yes, in parentheses, 1 plus 0.04, 0.074, divided by, it's quarterly, so divided by 4 to the power of, 4 times 4. 4 is the end, and 4 is the number of years as well. So yes, that's the power of 16. So 8,300 times, parentheses, 1 plus 0.074 divided by 4, close parentheses, the power of 16. 11, 128, 96. Yes. $12 was because it was monthly. This one was quarterly, so that's why it was 3 instead of 12. Or 4 instead of 12. When it was monthly, that number's 12. If it's quarterly, that's 4, because it's 4 times a year. Four quarters a year times 4 years is 16 total quarters. So our next step, which will lead us up to break pretty much here, might get time for you guys to try an example before we go to break. We are going to have Stacy. Stay, that maybe helps put the C in there. Invest $4,900 at 3.9% compounded monthly for 2 years. Find the amount of compound interest earned. This is the same type of question, just there's one extra step that goes on the end of it. We still need to find a future value. That future value is still going to be the present value of $4,900 times, in our parentheses, the 1 is just part of the formula, remember. 1 plus 3.9% is 0.039 as a rate, divided by, this is monthly, so it's 12, to the power of, 12 times 2 makes 24. So 4,900 times, parentheses, 1 plus 0.039 divided by 12, close parentheses, power of 24. 5296.83. Well, that is the future value, but we are asked to find compound interest. The compound interest is just going to be the future value minus the present value. So we have $5,296.83 minus $4,900, giving us a difference, $396.83. That is the compound interest. Time for you guys to try one. Find the compound interest on $6,100 at 4.2% compounded semi-annually for 5 years. Semi-annually means how many times a year? Twice. Very good. I'm going to give you guys a few minutes to see what you come up with there. So we start out by finding the future value, which will be the $6,100 times, parentheses, 1 plus 4.2% becomes 0.042 divided by semi-annually means twice a year. So divide by 2. You're thinking bi-monthly. The power of 2 times 5, which is 10. So 6,100 times, parentheses, 1 plus 0.042 divided by 2, close parentheses, power of 10, 750909. So then the interest, I'm going to subtract the 6,100, which is going to give us $1,409.09 is the interest. It is break time, so let's take 10 and we'll come back at 6:30. Okay, let's do one more example of these for you. Oops, it flaked on us again while we were out. Let me get my content showing. There we go. You bet. So, Tracy invests $5,700 at 5.9% compounded quarterly for 7 years. Find the amount of compound interest. I'm going to give you guys a couple minutes again. So we start by finding our future value, 5,700 times, open parentheses, 1 plus 0.059 divided by 4 because it is quarterly, to the power of 4 times 7 years, which would be 28. 5,700 times, parentheses, 1 plus 0.059 divided by 4, close parentheses, power of 28, 8588.72. So then we subtract the 5,700 present value to get 2888.72 is the interest. That is your answer. Now, because this is compounding, that is a higher rate of interest than what you would normally get in simple interest. You know, we saw in that first example we did, instead of 94.40, we had 95.56. You ended up with, you know, over $100 more, and that was just a 3-year period. So there's something called an effective rate. Just like with our simple discount notes, the effective rate is higher than the stated rate. An APR is the rate stated on the note. So if I tell you that Sam invests $12,000 at 6% compounded monthly. The 6% is the APR, that's the annual percentage rate. I'm going to finish this 6% compounded monthly for 2 years. Find the APY. APY stands for annual percentage. R was rate, Y is yield. In other words, that's the effective rate. For effective rate, or APY, we have to talk a little bit about the time. If the time is less than 1 year, we'll use the actual time. If the time is more than 1 year, we use 1 year. In the problem up above, what is the actual time? 2 years. So what that means is, since that's more than a year, we're going to only go for 1 year. That means we're only going to find the compound interest for 1 year. So our first step in the APY is to find the future value. In this case, since it's for more than 1 year, we're going to go for 1 year. So our future value is going to be, that was $12,000 times 1 plus 0.06. That was compounded monthly. So divided by 12 to the power of n times t. Well, n is 12, t is just 1. So that's the power of 12. So 12,000 times, parentheses, 1 plus 0.06 divided by 12. Close parentheses to the power of 12. So we got 12,740.13. Step 2, find the amount of compound interest. That's pretty simple. We're just going to subtract the original $12,000. Compound interest for 1 year, $740.13. Step 3, find the effective rate. And this is going to be using I equals PRT again. Effective rate always is going to end up using I equals PRT. Our I is the compound interest, $740.13. P is still our principal of 12,000. R is what we're trying to find. What's our time? Well, it was greater than a year, so we only went for 1 year. So our time is just 1 year. So this calculation simplifies a little bit. We have to combine the 12,000 with the 1 year. That's just 12,000. So we solve by dividing by 12,000. So $740.13. divided by 12,000. 0.06167 equals R. So we move the decimal 2 spots to make it a percent. 6.1678%. And unless we're told otherwise, we're going to round it to the 100th of a percent. That's 6.17% is our effective rate. So the period there was the time there, not the period. The time was more than 1 year, so we used just 1 year. What if the time is less than a year? Peyton invests $8,000 at 2.7% compounded. Come on now. We'll go monthly again for 8 months. Find the effective rate. So again, our first step is to find the future value. Now, is this more than a year or less than a year? Less than a year. Since it is less than a year, we will use the actual time. So the actual time is 8 months. So our future value here is our present value of $8,000 times 1 plus 2.7% is 0.027 divided by, now here's where a lot of people get confused. How many periods are in a year? It's monthly, so it's still 12 periods in a year, even though it's only 8 months, right? How many periods? 8, yes. Well, there's 8 months. It's 1 period a month, so it's just 8 periods. Technically, if you wanted to calculate it out, it's 12 periods per year times 8/12, which comes out, multiplies out to be 8, because 8 months is 8/12 of a year. Or you think about it, if a month is a period, if it's monthly, 8 months means 8 periods. You look confused. You got her? Okay. So 8,000 times 1 plus 0.027 divided by 12, close parentheses, power of 8. 8145.14. $8,145.14. What's our second step? Yeah, find the compound interest. So we subtract that present value. We get interest of $145.14. Third step. Slow down so you can catch up. The effective rate. So it is the 145.14 interest equals $8,000 is our principal times our rate, which is R, is what we're looking for. The time is 8/12. 8 months out of a year is 8/12. So we do have to combine 8,000 times 8/12. Is 5,333.33. Now again, I'm going to leave that in the calculator so I can reuse that number, because in my next step, I'm dividing by that 5,333.33. So I didn't clear it. I left it in the calculator. I'm going to type in 145.14 divided by second answer. ANS down by your equal sign. Like 0.027214 equals R. I'm going to move my decimal to make that a percent. Move it 2 spots. 2.7214%. And then I'll round it off to the 100th of a percent. There's my hundredths place. That one says it's going to stay, 2.72% is my effective rate. Any questions? Are we ready to try one? For the simple discount note? Because the proceeds were different than the principal. So, yeah, but you got to remember the amount of money you started with was the proceeds, not the face value. Here, the amount of money you start with is the face value. You start with $8,000. On that simple discount note, if it was an $8,000 note, they subtracted out the interest and you actually started with that lesser amount, which was the proceeds. Yes, the effective rate is always figured off the starting amount. And in the simple discount note, you didn't get the full amount to start with. It is. And the biggest thing here is that time thing. Less than a year is not a big deal, but if it's more than a year, you've got to remember only use 1 year. So let's say that, yeah, I'm going to have you guys try one. Invest $4,000 at 5.1% compounded quarterly for 75 years. Find the effective rate. Does the 75 years even matter here? No, because it's greater than a year. We're going to use 1 year. Okay, I'll give you guys a couple minutes. So step one is to find that future value. That'll be 4,000 times 1 plus 0.05 divided by 4, because it's quarterly. To the power of 4 times 1, because we're going to go for 1 year, right? It says it's more than 1 year, so we go for 1 year. So that's just going to be the power of 4 there. Oops, should be 5.1, you're right. So 0.051, thank you. So 4,000 times, parentheses 1 plus 0.051 divided by 4, close parentheses, the power of 4. 4207.93. Now step 2 is to find the compound interest, so we subtract that present value, the beginning balance, to get 207.93 is the amount of interest. So then the effective rate is at 207.93 equals the 4,000 times R times 1, because we went for 1 year. Now I'm not going to go through the act of combining 4,000 with 1. You know that's 4,000. So we're just going to divide by the 4,000. So 207.93 divided by 4,000. 0.051983. Move that decimal point 2 spots to make a percent. 5.1983%. Round it to the 100th of a percent. That is 5.20% is our effective rate. Anybody get that? You had the wrong compound. Okay. That's because it's monthly, so it's compounding more often. It's maybe slightly higher, yeah. Yep. Yeah, if it's over a year, you ignore the time and you just use a year. Yeah. That's why I put the 75 in there, just to kind of be absurd. Find the effective rate for $7,000 at 4.2% compounded quarterly for 9 months. I'll give you a couple. Okay, so we're going to find our future value. It's going to be the $7,000 principal or present value times parentheses 1 plus 4.2% is 0.042 divided by 4 because it's quarterly. Now here's the tricky part. It's to the power of, 3 is what it's going to be. It's 4 times 9/12, which does give us 3 is our number of periods. So 7,000 times parentheses 1 plus 0.042 divided by 4, close parentheses, power of 3. 7 to 2282. It's our future value. What's next? Subtract that present value or the beginning value to get $222.82 in interest. And then I equals PRT. That 222.82 is our interest. Principal was $7,000. We are looking for R, and now we do have to consider the time is 9 months, so 9/12. So we do have to start out by combining the 7,000 times 9/12. So 5250. And then we solve for R by dividing by the 5,250. So 222.82 divided by 5250. 0.042442. And then, of course, we make it a percent. Move the decimal point, 4.2442%, and we round to the 100th. That's 4.24% is our effective rate. Any questions there? Okay, so in your book, on page 463, I believe it is, there is a shortcut table. Now, like any shortcut, this shortcut only works in special circumstances. You'll notice this table is labeled the future value or compound amount of $1. So this is saying is for every dollar, this is what the future value would be. Okay, so let's take, oops, what's going on there? Okay, so let's take page 463, $5,000 at 8% compounded quarterly for, let's go 5 years. Using our formula, that future value is going to be 5,000 times 1 plus 0.08 divided by 4 because it's quarterly, the power of 4 times 5, or 20. Giving us a future value of 74,2974. Well, this table would allow us to calculate this. There are two things that you need for the table. One is rate per period. Rate per period is actually right out of the formula. That's R over N. But I don't have to do it as a decimal. It's just 8% divided by 4 periods in a year is 2%. That's my rate per period. The second thing I need to make the table work is the number of periods. That's also right out of our formula. That's N times T. So for this example, that's 4 periods per year with quarterly, times 5 years. That's 20 periods. So you would look at that table on page 463. You would look on top at 2.00%. You would follow that column down to 20 periods on the left side, and you would get 1.48595. That is the compound interest future value factor. That is the future value. So you find 2.00 on the top. You follow that column down to hit 20 on the left side. You get 1.48595. You went down too far. Stay up on the top of the table. You jump down to the second table. Yeah, that table ends at the middle of the page. There you got it. So what that means is we could have found the future value here by taking our 5,000 present value times 1.48595. This may not be exactly the same. And you can see it's slightly different. We get 74,2975. Here we're off by a penny. In many cases, we'll be off by several pennies because this here factor only goes to 5 decimal places. This formula is exact. This is the exact amount. This is always going to be rounded by the number of decimal places in this factor. Does that make sense? Now, obviously, this table is easier to use. Yeah, we'll try an example here. The advantages are it's easy. That's really the only advantage. Disadvantages. The big disadvantage, you have to have the table with you. I don't think any of you are going to carry the textbook around with you for the rest of your life. Every day, you're probably not going to get a tattoo on your forearm of the compound interest table. The second is it only, if you can tattoo, if it is permanent ink tattoo, you can tattoo whatever notes you want on your forearm for this class. The second disadvantage is it only works for round values, round numbers. What do I mean by that? Well, if this was 7% compounded quarterly, 7 divided by 4 is 1.75. Do you see that column, 1.75%? No, they don't have that on there, do they? So it only works for numbers that are going to give us a nice round percent when we divide them out. Also, it only goes up to 30 periods. That's also an issue. The formula will always work, no matter what the numbers are. This table only works for specific values. So I'm going to let you guys try one. Now I'm just going to put it out here. Let's do $7,000 at, let's do 6% compounded monthly for 2 years. I'll give you a second. So 6% compounded monthly, our rate per period is 6 divided by 12, or 0.5%. Our number of periods monthly for 2 years, 12 times 2, or 24 periods. So out of the table, you look in the 0.5% column, you go down to 24, you get 1.12716. So our $7,000 times 1.12716 is 7890.12. Did anybody use the formula to double check it? What'd you get, the same amount? Okay, nope. No, you don't. You can just grab the number right off the table. So you found your rate per period, which is just your percent divided by the number of periods in a year. That gave you the 0.5. So then your number of periods is that N, that number of periods per year, times the number of years. So 12 periods a year times 2 is 24. So you find the 0.5 on top, which is the first column. You follow that down to 24. Yeah, so you get the 1.12716 times the 7 grand. You get the exact same. Yeah, since it's only a couple of years, usually then it'll be the same or within a penny. Now, there is something called compounded daily. There's also continuously compounded. Continuously compounded was a fad back in the late 90s, early 2000s. You know, they advertised every moment of every day your interest in your account is compounded. And it was, but it was a very complex calculation. It's kind of faded. There are still some things that are continuously compounded, but not so much anymore. We're not going to worry about continuously compounded for this class, but it might be something you would run into if you went on to a finance class or something like that. You might see continuous compounding. Daily compounding really isn't that horrible. Let's say that we have $5,000 at, let's do 2.5% compounded daily for, let's say, 180 days. This happens for short-term loans. If you have a short-term high-risk loan, they will compound daily. Yes, those are usually daily compounded, yeah. If you do a paycheck loan, those are usually daily compounded. So they might be charging, by statute, there's a maximum percentage they can charge. It's like 39%, by the way. It's ridiculously high. They cannot, the amount of interest on the total loan cannot be more than 250% of the principal. So at the end of the loan, you can't end up paying more than 2.5 times. What's that? Yeah, it's a vicious cycle. That's another one that would put me up on my soapbox. We don't have that kind of time. But anyway, let's find that future value. Well, we could use the formula. Future value is $5,000 times 1 plus 2.5% is 0.025 divided by, it's compounded daily. How many times a year is that? Good question. Is it 360 or 365? I don't remember which way this book does it. So let's do it both ways and see if we come out, match the table. To the power of 180. I believe they use 365, but we're going to double check it. So 5,000 times parentheses 1 plus 0.025. We're going to start out with the divided by 365. Power of 180. So 506202. Now let's find the result out of the book. On page 471. Your book has a daily, it actually goes over to page 472 as well. Your book has a daily compounding table. This daily compounding table is much more complex to use. So I'm going to put some steps down here. The homework in my math lab, if they do daily compounding, they will always use the table. For any other compounding, yeah. But if that happens, if you prefer the formula, because I prefer the formula, if you use the formula and my math lab says you're wrong, send me an email and I will correct it. If it's homework, don't worry about it. Just know that you are right. There's a couple last, yes. Starting at this point, this is where I have to start going through, and I actually have to start going through and I have to grade all the quizzes manually. I have to go through and see, because my math lab will only accept one answer, but there are other correct answers depending on which formula you used. So, well, in my math lab, if it tells you it's wrong, when you go back to look at your answers, the answer it shows you in the box is the correct answer. If you put your cursor over the top of that and hold it, it'll pop up in a little pop-up box what your answer was. If they're within pennies, you know you're right. Yeah. So in the daily compounding table, step 1. Now you'll notice what this is. The other table said compound interest on $1. This says compound interest on $100. So that means we take our principal, our present value, divided by 100. So for here, this is $5,000. Divided by 100 is 50. That's what we're going to use with the factor in this table. Step 2, we find the table factor. So the table factor, we use the 2.5%. And the 180 days, we combine those to get what? We get a factor of 1.240465. Okay. Step 3, we're going to multiply steps 1 and 2. So we got the 50 times 1.240465 to get 6202. This amount that we found here is the amount of interest, not the future value. So to get the future value, that's step 4. That's our present value plus the interest. So that'll be our $5,000 plus that 6202, which is $5,062.02. Is that what we had? Yes, it was. So they did use 365. That's what I thought. Use the formula. Yeah, if you're within pennies, just assume you're right. And I will regrade the quizzes by hand. From the last 4 quizzes, I regrade by hand on all of them. So don't even worry about it on the quiz. When you go back and check your quiz over, if it says it's wrong, but you're within, sometimes even as much as $1.50 on larger numbers. Yeah. Yes. Yeah. On my answer key for the last test, I have both answers down. Yes. It is 7:20, so let's take our second break. Let's do 10 and we'll back at 7:30. So as we're coming out of a break here, give that one a shot. See if you can use that daily compounding table. Let's see how we come out here. So I'm going to use the table, but for those of you using the calculator, let's see how they compare. So we start out with the $8,000. Of course, we have to divide that by 100 to get 80. Then we look in our table, 1.50% and 60 days. We get a factor of 0.246875. So then we multiply those two numbers. Get interest of $19.75. We add that to the original $8,000 principal to get $8,019.75. If you use the formula, what'd you come up with? Same thing? Perfect. Okay. So for our last hour, our last thing we need to learn about is something called present value. What we've been working on so far, if we look at our timeline, we knew the present value. We calculated the compound interest. To find the future value. For this next topic, so what we're doing now is we're starting with that future value and we are looking at the compound interest to go back to figure out how much we would have to start with. Why would we ever want to know this? Well, let's say that something happens. You have a large amount of money available to you right now. Usually maybe an inheritance or win a small lottery or a bonus or a severance package when you lose a job or something like that. You have a large sum of money available right now. And you want to know how much should you save at, let's go 5.3% compounded monthly in order to have $7,000 in 10 years. So you want to have $7,000 sitting there at the end of 10 years. You have a little bit of cash right now. This might even just be a bigger than normal income tax refund coming in. We know the future value. We want that future value to be $7,000. So we're going back to see, what does our present value have to be? What do we have to start with so that compound interest will add up to $7,000? Yes, planning ahead, yeah. So what we're calculating now is the present value. Bless you. So our formula now, instead of future value, it's present value is equal to the future value. And here's the only difference in the formula. Instead of times, it is divide. We're going the other direction. Parentheses, 1 plus r over n, close parentheses, the power of n times t. The exact same formula, the only difference is this is divide instead of multiply. So for this example, that present value is the $7,000 divided by parentheses 1 plus 0.053 divided by compounded monthly, so divided by 12, close parentheses. This will be the power of 12 times 10 years. So the power of 120, perfect. So 7,000 divided by parentheses 1 plus 0.053 divided by 12, close parentheses, the power of 120. 412505. So what that's saying is right now you would have to put away $4,125.05. So you would have $7,000 in 10 years at that interest. Yep. Yep. The reason I write the formulas like this is because this is how you would punch it in the calculator. In the book, they would write this formula PV equals FV over 1 plus R over N to the power of NT. Well, the calculator doesn't work that way. So you got to figure out how to enter that in the calculator. Yeah, so that's why I do it this way, because this is the way you would enter it in the calculator. And in the next 2 weeks, there's going to be more formulas, and those formulas are even more complex. And the way the book presents those formulas is all screwed up. I mean, you'd have to do like 7 different steps. Yeah. 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 So, and that's why I present it that way, is it's a more direct way of doing it rather than having to interpret math jargon into what you actually have to do. So let's look at another example here. Let's say you are planning, you have a child that is born. So in 18 years, you want $20,000 for your child's college tuition. That's what financial aid is for, right? How much would you invest now? Let's say you've got a grandparent or somebody who wants to put money towards it, or an inheritance, or something that they want specified to go towards a college education. How much would you invest now at, now that's 18 years, so we're gonna get a better rate. Let's do 9.8% compounded quarterly. If you go to an investment planner on an 18-year, you can get guaranteed rates on bonds of like 7 or 8% right now. Yeah. So the present value that we are looking for will be the $20,000 divided by, open parentheses, 1 plus 9.8% will be 0.098 divided by quarterly, so 4, right? To the power of 4 times our 18 years, which is what? 72, right? So let's divide this out. 20,000 divided by, parentheses, 1 plus 0.098 divided by 4, close parentheses, power of 72. $3,500.81. Yep, you put that in today and you let it sit there for 18 years to $20,000 at 18 years at 9.8%. Yep. Not impossible to do. I cleared 24% on my investments last year. In 30 years, you want $200,000 to retire. You're not going to make it, huh? How much should you save now? Now, in a 30-year investment, I should say in the stock market, the average annual gain on any 30-year period, that includes periods that included the Great Depression in the 1920s and 30s, and periods that included the big crash in 2008. Any 30-year period averages between 12 and 13% annual gain. So if you have a proper investment, that's not hard to get over 10%. Any investment that's put into the stock market in an index fund even would do it. So how much should you save now at, we're going to just say 10%. That's on the low end, really, if you're willing to take some risk. At 10% compounded quarterly. I want you guys to figure this one out because I think you'll be surprised at So we start out the 200,000 divided by parentheses 1 plus 10% is going to be 0.10 divided by quarterly, so 4, close parentheses, power of 4 times 30, which is 120, exactly. So 200,000 divided by parentheses, 1 plus 0.0, or 0.10, divided by 4, close parentheses, power of 120. 10, 331, 57. So a $10,000 investment right now at 10% interest would give you 200,000 in 30 years. That's the power of being young. True. But if you did that every year for 5 years, well, let's look at that. Average cost of living increase was between 2 to 3%. Now it's about 1.5 to 2% a year. Let's go 2% cost of living increase. That is 2% compounded annually. Yeah, that $10,000 is just once. If you did that every year for 3 or 4 years, it adds up. But that's 2% compounded annually. How much do you think you would be able to survive on right now for a year? Yeah. Well, I mean, let's look right now. If you wanted to maintain your current standard of living, 20,000 do it. 30,000. I'm talking tax free. After taxes. No, I'm talking right now though. Yeah. Well, I mean, wipe out the kids. I mean, I don't mean it that coldly, but forget about the kids. Hopefully, they're out of the house before you retire. Yes. Could you survive on 20,000 a year? You'd still have property taxes. I mean, talking right now, if you had no kids to deal with. Yeah. Let's do 30,000 a year. So 30,000 a year. This is just a future value calculation. Times 1 plus that 2% is 0.02. Compounded annually, so divided by 1 to the power of 30. That's 30 years. So 30,000 times parentheses, 1 plus 0.02. I don't need to put in the divided by 1, but I will. Power of 30. 54,340. So a $30,000 lifestyle right now is going to be a $54,000 lifestyle in 30 years. Basically, figure it'll close to double. Your cost of living will close to double in 30 years. At the current rates, maybe a little less than that because it's been like 1.7, 1.8% the last couple of years. Yeah, assume probably higher, but so figure double what you live on in a year now. But you also assume there's things that are not going to be there, like kids. Hopefully, you're no mortgage payment, but you may have a rent payment or still have property taxes, one of the two. There you go. But there's also increased medical costs, prescription drugs, and stuff like that. So there's some increased costs. There you go. Now, there is a table in the book on page 477 that deals with present values. You would do the same type of thing. You would look up that factor. And if you are using the factor, the present value is the future value times the PV factor out of the book. So the formula is divide, but the factor is always times. because my math lab does a ton of examples with that, I'm not going to do many examples in class here. I'm going to do one example of that formula. So let's say find the present value of $5,000 at 6% compounded. I gotta look at that table just to make sure I got a percent that's gonna be in the table. Just like our future value table, the big weakness here is not all the percents are in it. We'll do compounded monthly for, I guess, 2 years ago. So that is our rate per period is 6% divided by 12 because it is monthly. That is 0.5%. Our number of periods, 12 per year times 2 years is 24 periods. So we look those up and we will get a factor of 0.88719. So we would take our future value of 5,000 times that. So you would have to save $4,435.85 to have $5,000 in 2 years at 6% compounded monthly. The formula will give you something very simple, very comparable to that. Like I said, I absolutely despise the tables, but if you like them and you use them, my math lab uses them. I do accept them on the test. Trying not to show prejudice, but yeah, I despise them. So, no, that's why I stress the tables, or I stress the formulas over the tables. I show you the tables, but I stress the formulas. My math, well, I pick the problems in my math lab. The problem is my math lab, most of the problems use the tables. I found as many as I could that use the formulas. There just aren't that many in there. Short of writing my own questions for it, which is very time consuming. So that's why I just grade them by hand. Do the formula if you want to, and I'll just regrade them by hand so that you get credit for them. Yeah. So there is a new quiz due tomorrow, Thursday at 11:59 p.m. There's new homework due for next week, next Wednesday. This stuff, it's very similar one way or the other. So rather than spend another 20 minutes doing examples, I think it's really best to let you guys dig in and give them a shot. The most difficult concept in this week, I think, is that effective rate. And remember, with the effective rate, and this is the part that people will forget, it's all about the time. What's our rule on the time? Okay, if it's less than a year, we use the exact time, the given time in the problem. If it is more than 1 year, we use 1 year. Oops, get back here. Now, you may run into a problem. Okay, you will run into a problem because I know I put one in there where they don't give you a dollar amount for effective rate. Find the effective rate for 8% compounded monthly for 5 years. Well, first of all, what time are we going to use here? Yeah, that's the question. So we're going to use 1 year because our time is bigger than more than a year, so we're going to use 1 year. There is no principal given here. There's no amount, no dollar value given. Well, guess what? It doesn't matter. What's that? Well, we can use whatever dollar amount we want. I usually use $10,000. The reason I use $10,000 is it's a nice round number and it gives us nice round numbers. Let me show you. So our future value would be that $10,000 times 1 plus 0.08 divided by 12 to the power of 1 year, right? 12 times 1 or 12. So 10,000 times parentheses 1 plus 0.08 divided by 12, close parentheses, power of 12. Get a future value of 10,830.00. That was 0.995, which rounds up to 0.00. So that means the amount of interest, subtract the original 10,000, is $830 in interest. That's our compound interest. So we have the 830 equals 10,000 times R times 1 and we solve it by just dividing by the 10,000. Now again, we would combine the 10,000 and the 1, but we all know that's just 10,000, so I'm skipping that step. If it were less than a year, then we'd have to make sure we combined that principal times the time. There might be a problem similar to this in the homework. It'll still work. Yep. Let me show you. So I get 0.083, right? Which is 8.3%. What if I pick $2,000? Well, it's still going to be 1 plus 0.08 divided by 12 to the power of 12. So we get 221, 65.999, so 2166. So our interest, subtracting the 2,000, is $166. So 166 equals 2,000 times R times 1 year divided by 2,000. R equals 0.083, 8.2%. The effective rate really only depends on the percent and the compounding. It has nothing to do with the principal. So you can pick any number you want for that principal. Okay, I'll let you guys go. The computer lab next door is available. Computers at the other campuses are available if you want to work on homework or quizzes. I will be in here till 8:20.